What is a vector? In Euclidean space, we might write a vector like this. Starting at the origin, the first coordinate tells us how to move horizontally. The second coordinate tells us how to move vertically. Together, these two movements determine a single directed arrow. They describe both a direction and a displacement in space. But how long is this vector? To find the length of this vector, notice that its components form a right triangle. The horizontal side has length 3, the vertical side has length 4, and the vector itself is the hypotenuse. By the Pythagorean theorem, the square of the vector's length is the sum of the square of its components. So we get 3 squared plus 4 squared. This gives 9 plus 16, or 25. Taking the positive square root, we obtain 5. We call this number the norm of v. In Euclidean space, the norm measures the length of the vector. The same reasoning works for a general vector v. And in Rn, we square every component, add the results, and take the positive square root. But notice the expression inside the square root. We can write each square as a product. This expression is the inner product of v with itself. We now know how to calculate the length of a vector in Rn. Its norm is the square root of the sum of the squares of its components. But let us look more closely at the expression inside of the square root. Each square is simply a component multiplied by itself. So v1 squared can be written as v1 times v1, and the same is true for every component. We give this sum a name. It is the inner product of v with itself. The two entries inside the angle brackets are the two inputs of the inner product. Since this is exactly the expression under the square root, we can write the norm more compactly like this. The inner product of a vector with itself is its length squared. For the vector v equals 3, 4, the inner product of v with itself is 25. Taking the square root gives us the norm of v equals 5. Here we place the same vector in both input positions, but what happens when the two vectors are different? Previously, we placed the same vector in both input positions, but the inner product can also pair two different vectors. Let x equal 2, 3 and y equal 4, 1. We will use these two as an example. First, pair the first component of x with the first component of y. Multiply them together. Next, pair the second component of x with the second component of y. Multiply them together. Finally, add the products. So the inner product of x and y is 2 times 4 plus 3 times 1. That's 8 plus 3, which equals 11. Notice that the inner product takes two vectors as inputs but produces one real number. Its output is a scalar. Now replace the numerical components with general coordinates. Let x equals x1, x2, and let y equal y1, y2. The same rule gives x1, y1 plus x2, y2. Therefore, in R2, the inner product is found by multiplying corresponding components and adding the results. In Rn, the same pattern continues through all n components. Multiply corresponding components and add all the products. In summation notation, this is the sum from I equal 1 to n of xi, yi. When two inputs are the same vector, each component is multiplied by itself. We end back at the sum of squares from previously, and therefore the norm of x. Calculation is algebraic, but the number it produces contains geometric information. The inner product of our two vectors is 11. Since 11 is positive, the vectors point in broadly similar directions. For example, let x equal 2, 1 and y equal 4, 2. These vectors point in exactly the same direction. Their inner product is 10, which is positive. More generally, a positive inner product means the angle between the vectors is less than 90 degrees. Now, let x equal 1, 0 and y equals 0, 1. These vectors are perpendicular. Their corresponding products are both 0, so their inner product is 0. For non-zero vectors, an inner product of 0 means the vectors are perpendicular. Finally, let x equal 1, 0 and y equal 0, 1. These vectors point in opposite directions. Their inner product is negative, and more generally, a negative inner product means the angle of the vectors is greater than 90 degrees. So the sign of the inner product divides the geometry into three cases. Positive corresponds to an acute angle, 0 to a right angle, negative to an obtuse angle. We can see all three cases in one continuous motion. While the angle is acute, the inner product is positive. At 90, it becomes 0. After 90, the inner product becomes negative. The sign tells us whether the angle is acute, right, or obtuse, but how exactly does the value of the inner product depend on the angle? Keep the lengths of the two vectors fixed and change only the angle between them. The quantity, the length of y times cosine theta, measures how much of y points in the direction of x. The inner product is the length of x multiplied by the amount of y pointing in the direction of x. When the vectors point in the same direction, the angle is 0. Since cosine of 0 degrees is 1, the inner product is as large and positive as possible. At 90 degrees, the projection disappears. Neither vector points in the direction of the other, so the inner product is 0. Beyond 90 degrees, y points partly against the direction of x, so the inner product becomes negative. At 180 degrees, the vectors point in exactly opposite directions. The sign pattern from before is now explained by the cosine of the angle. We now know how to measure the length of a vector, but how can we measure the separation between 2 points? Let the 2 points be A and B. The vector that moves us from A to B is their difference. The points represent positions. Their difference represents a displacement. The displacement vector B minus A has both length and direction. Distance keeps only its length. Since the norm of a vector comes from its inner product with itself, we can also write this. So the inner product gives us length, and length gives us distance. For example, suppose the difference between the 2 points is the vector 3, 4. This means that moving from A to B requires a horizontal change of 3 and a vertical change of 4. The distance between the points is 5. If B moves while A remains fixed, the displacement vector changes. Its norm changes with it, continuously measuring the new distance from A to B. Now suppose a point remains exactly distance r from A. As the point moves, it traces a circle around A. But what do we obtain if the distance is less than r? We measured the distance from a fixed point A to a moving point x. Suppose that distance always equals r. Every point on this boundary is exactly a distance r from A. In 2 dimensions, these points form a circle. Now move x inside the boundary. Its distance from A is no longer equal to r, it's less than r. This inequality describes every point inside the boundary. A point inside has a distance less than r, so it's included. A point on the boundary has a distance equal to r, so it's not included. A point outside has a distance greater than r, so it's also not included. The collection of all points whose distance from A is less than r is called the open ball radius centered at A. An open ball is a mathematical way to describe all points sufficiently close to A. The radius determines how much of the surrounding space is considered nearby. A smaller radius gives a smaller neighborhood, while a larger radius gives a larger one. In 1 dimension, an open ball is an open interval. In 2 dimensions, it's the interior of a circle. In 3 dimensions, it's the interior of a sphere. The picture changes with the dimension, but the definition remains the same. The inner product gives vectors length and angle. Length allows us to determine distance. Distance allows us to describe neighborhoods. A neighborhood is built by collecting all points whose distance from a chosen center is sufficiently small. Distance is measured by taking the difference between 2 points and finding the length of that difference. The length of a vector comes from its inner product with itself. And the inner product also tells us about the angle between 2 vectors. We began with the 2 coordinates 3 and 4. The Pythagorean theorem gave the vector a length of 5. The inner product turned coordinates into geometric information. It gave us length and angle. Length gave us distance, and distance gave us neighborhoods. These ideas prove that the language of closeness and change that we will use to study functions, derivative, and eventually manifolds. This is how a list of numbers begins to describe the geometry of Euclidean space.